All right. So how you guys doing today? Good. All right, perfect. So the today we're gonna talk about the NMR again. So simply what I'm gonna do is just reviewing what we did on Wednesday again. So we're doing NMR, but I'm going at this time I'm gonna explain very slowly, and very detailed, like every bit of the information. So before we move on to the actual problem, at least we can have some idea what's that really about. Nuclear magnetic resonance spectroscopy. So this is also another type of spectroscopy, meaning we're gonna use some form of a light. It actually means another form of energy, and we're gonna interact the energy with the matter, like a compound, and see how does the signal or information we get from there. We analyze it with this device we call spectroscope. But we actually call this again NMR, because we're actually going to use a nucleus in the compounds. So if you look at the atom, you guys remember what's in the center, right? In the center of the atom, this is where you can find the nucleus. Obviously, this is made of proton and neutron. So at the center in the atom, it's positively charged. That is why you have other electrons also kind of moving around the nucleus that makes the whole atom. And as you know, this smallest part is just empty space there. And then we use this nuclear, it says magnetic too. So magnetic is just like kind of a vector field you can have with some magnetic property of the matter. So what I mean by that is this magnetic property can be just happen. It only happens whenever you have a motion of something that is charged, either ion molecule, something, either plus or minus. Okay? If there is some charged something, if it's moving, it will generate the magnetic properties. It also generates some magnetic field, so they can have a certain amount of force they can move around based on where they are in the magnetic field. So, meaning we're actually going to use the nucleus in this compound, and how they're gonna make how much of the magnetic property they have by motion, and so we can use this information for spectroscopy. So what they know is the nucleus is spinning. You guys remember electron spin? The fourth quantum number is electron spin, right? Like at that, just the nucleus also do the spinning too. So if it's a spinning, it makes motion. But also it's a positively charged, because it's nucleus, proton, and neutron, right? So charged, the nucleus spinning, it generates some magnetic property there. So if that makes sense, let's try to use the information. Because of the magnetic spin can be canceled them each other in the nucleus. What I mean by that is the protons, right? That should be the odd numbers of protons, be the odd numbers of neutrons. So you can have a proper charge. They can do some motions that have some magnetic properties there. So this is why this is the best one to use, which is the hydrogen, because hydrogen has just one proton, one is odd number 2. That's good. But unfortunately, we cannot use carbon-12, because as you know, atomic number for carbon is 6, meaning numbers of protons of carbon-12 is 6. So it's an even number. That makes also atomic mass number is 12. So 6 neutron, 6 proton, they're all even numbered. So we really can use it. But luckily we have very small abundance, but still carbon-13 that will show you 7 neutrons instead of there. So these two are the other things that we normally use. You can use all the elements with all numbers, proton, neutron, But as you can think about the organic compounds, it's mainly what? Hydrogen and carbon. So this is the best one we can do the animal, okay? It makes sense so far, right? Good, okay, so if that is the case, here's the thing. Whenever you have some nucleus, magnetic spin in random directions, okay? Random direction. Because we know how there's a magnetic spin into randomly just directed here. But if we apply some additional, external magnetic field, maybe in this way, okay? What happens to those nucleus magnetic spin is some of them will align just parallel to as the external magnetic field, but the other goes down to anti-parallel position. So obviously, this is the one go against the external magnetic field. But this is more unstable, meaning this is higher in energy level. This is lower in energy level if this go parallel with it. So we call this alpha spin, we call this beta spin. So here's the thing. Just like the electron you learn in Jenkins 1, if you have a certain electron to get to another level, which we use the quantized energy level, you have to put some energy into it in the form of light. In this case, the gap between is perfect for the radio frequency wave pulse. So we do this electromagnetic spectrum here so they can have enough energy to jump to the beta spin position there. When they get to there, they can also go back to the alpha spin again when they emit that amount of energy as well too, just like we did on the electron injection. And when we catch this in the detector, we're going to analyze the data for the structure or the carbon-hydrogen framework in the compounds. So here's why. Now you guys wonder, okay, so if it's the same carbon, same hydrogen, what will be doing this? Because this gap between these two will be always the same. It's the same carbon, same hydrogen. Well, we bothered by this one so much, so they can have a same signal on the same spot. There's no information there. The thing is, this energy state is not always the same for the same carbon, because this can be very sensitive on its environment. Okay, so think about it. We're talking about the one positively charged nucleus magnetic spin aligned with the external magnetic field, but you're forgetting about another thing that is charged too. That is what? Like I said before, there's an electron there too. Okay, so electron there too. Okay? So electron also negative charge is an electrospin, magnetic spin there. It also has some magnetic property there too, meaning we have a successfully aligned with it parallel or anti-parallel position depending on the electron density around this carbon. It may show different energy gap. The two energy level, right? Different energy level will show you the signal won't be on the same position because of the electron density. And now you guys wonder now, what do you mean? They're same carbon, they should have the same number of electrons around it, right? That is wonder, right? But think about they are in molecule form. So just one example here. If you have a carbon on this one particularly, and carbon on this one, okay? This carbon also have a certain electron density. While we pointing exact location of the electron in the Lewis structure, in this way, I kind of want you to look at this one as like a wave function wise. Meaning, we just gonna see the electron not as number, but like a chance, high chance or low chance. Meaning, if it's like a clouded electron density or just fade electron density or not so much. Okay. So in this case, as you can see, this oxygen is very highly electronegative, meaning oxygen is higher force to attract the electron toward themselves. So if you have a carbonyl groups over here, electron density wise, you have a much darker electron cloud around the oxygen than the carbon. So that's why you have a carbon is less shielded by electron, because most of the electron are kind of pulled towards the oxygen, because this one has a stronger force to attract them. So this will be less in electron density around this carbon. So this is what I mean by environment. Environment of the carbon in the compound may differ because of the neighboring carbon, neighboring oxygen, neighboring nitrogen, and so forth. So this is a kind of fundamental idea that how we're going to use the NMR to find out how those are framed in the compounds. Make sense so far? You good? Okay. If that is the case, this one is relatively speaking more dense in electron, because hydrogen is less electronegative than carbon. So compare these two, this is less shielded by electron, but this is more electrons around it, so it should be more with electrons here. Then that makes different gap and energy level because the electron density will interfere with the external magnetic field. So if it's more shield, you need to have a stronger magnetic field to get to the resonance field. Okay. So if that is the case, now we know, even though it's the same carbon 13 or same proton or hydrogen, it may show you different signal, so you can analyze it. Okay, this is one way. Okay. So when you look at the NMR graph, we're not going to do absolute measurements, but we're going to do relative terms of measurements. Meaning, you're going to have one compound as a standard points, like a 0 point in parts per million. I'm going to explain why it's called parts per million, okay? So parts per million, parts per million, meaning it's parts of something. So it's a relative term. It's not like a 1, 2, 3, 4. We're not going to measure the absolute value there now. We're going to measure the relative value compared to the ones in one compound that we use TMS. This is a tetramethyl methylsilane. It just looks like this. Okay. This is a perfect sample for the standard in NMR because of the several reasons. If you do carbon or proton or hydrogen NMR, that will show you very shielded. So if you go to the left to the right, this is where we call upfield. And this is where you see the more shielded carbon or hydrogen with the electrons. So it's more shielded with the electron density. Here, if you go from right to the left, this is where you can see downfield, meaning it's less shielded by electron. There's not much electron around that carbon or hydrogen, okay? So it's de-shielded. Okay? So if that is the case, here's the thing. This will be good example compound that is the highly shielded by electrons and should be the far outfield position, so we can use it as a standard point. And also, because if you look at this one, carbons are bound to hydrogen. So carbon is quite happy because they're competing with very weak components for electron. So they're well shielded, so it could be here. And also, central atom is a silicon that has also very lower in electronegativity than carbon. So carbon also happy with the central atom too. It's very shielded with a lot of electron. This is a really good sample that we can set as a standard on the upfield position. So this TMS position we set from 0. So that means we're gonna compare that number to your sample so you can have some signal to analyze. Okay? And also what is so good about this one is you can look at those methyl groups on here, around this central atom here. Those carbon and the hydrogen that we call equivalent carbon and hydrogen. Meaning, so equivalent means they have the same environment, meaning same electron density around it. Because there are relative term, they're same environment. If you look at this carbon right here, or this carbon here, this carbon has affected by central silicon atom here, and all the other neighboring carbon methyl groups on the central atom toward to them, right? So if I'm standing right here, I'm looking at the central atom in the middle, I see other 3 methyl groups on there, the back, left and right. For me, that's how I see it as a carbon. But if you look at for this view, will be the same. You looking at toward to the central atom here, you also see another methyl group on the back, left to the right. This carbon, same. Back, left, right, back, and left. So those 4 carbons are at the different position, but frankly speaking, they have the same environment around it. Their same hydrogen 3 around it, same central atom, same position as the other methyl groups. So whenever you measure the signal for those carbons, will be on the same position. Because like I said before, those 4 carbons have the same environment, meaning same electron density. Make sense, right? And also hydrogen Y, they also have the same position on the same carbon. So to them, they also have a very same environment around the same equivalent carbon as well. So whenever you do either proton or carbon, you're going to have a very good set point you can compare to, which is standard on the very upfield location of your NMR. So it'll be easy to analyze from the one on the other downfield values over here. Makes sense, right? Can I move on? We good? Perfect. All right. So I'm going to go very slow at this time, so just stop me anytime. Okay, so technically speaking, so another thing you just need to know is, like I said, we're actually going to analyze the data by looking at the amount of energy we put in and they emit once they go to the alpha spin. So another thing I just want you to remember is this is low frequency energy. I'm saying low frequency energy because the energy of the electromagnetic radiation is dependent on the frequency based on the Planck constant. Anyway, so just remember this one too: low frequency, higher frequency too. Meaning lower energy, higher energy required to find this resonance form and fall back so you can have the position of some air that would compare to this one. So this is what we call delta sign in parts per million. So this is something you don't have to know, but if you just try to remember, like I said, all different device for NMR, like we have an NMR like a 600, 400, 500, they use different strength of magnetic field, okay? So if you change the magnetic field, external magnetic field, the alpha spin and beta spin position will be larger and larger if it's stronger and stronger magnetic field. Then also this is a good reason why if we just use a relative term of just the measurement of where the peak will be located, it will be still same anyway, whatever the strength of the magnetic field you use there. Okay? So that is why we have the delta sign over here that will show you even observe the peak around the hertz from PMS. This is just 0. So we just set it as 0. There's no why we set 0 because this is just how we set it. And if there's like a 300 megahertz, the radioactive, not radioactive, sorry, the radio frequency. And that device, because this is only based on like 7 Tesla. So Tesla means the unit for the strength of the magnetic field. But if you change this one to 21, it actually triple those number and those number at the same time. So number you see over there is this is divided by a million, because mega means million. This to be 4. So even though you use a 7 Tesla power NMR or 21, you're always going to see this delta location compared to the TMS. This is more D shield on this side than TMS. So over here, but it still be 4 ppm anyway for either you do it 7 or 20. Because if you just triple here, it still be what? 3600 divided by what? 900. It's be 4. So this is the reason why we use this relative term for analyze the NMR, which won't be on the exam, but be really good to understand whenever you do the practical problem solving. So now I'm going to move on to the actual problem. So I'm going to show you how we're going to do this together. Okay. So the first thing, what we're going to do is carbon 13. If you look at the textbook with this, the PPT slide, we do carbon 13 because this is relatively speaking easier to analyze than proton. I'm not saying proton is really difficult to analyze anyway, but let's start with this one. It's a bit more simple. Okay. So if that is the case, I can give you one example that I also give you on Wednesday. Here. So you have 4 carbons over here, and I can tell they are all in different environments because this is near to the oxygen. You have a 2-terminal carbon, but this carbon is close to the neighboring carbon to the oxygen, and this is between 2 carbons. So each carbon has, relatively speaking, different environments in the molecule because of this one. So if there is no carbonyl groups there, it's just butane, there are going to be only 2 signals because of this. So you have a 2 terminal carbons are here, right? 2 terminal carbons are here, right? And there are 2 inner carbons which will only have what? 2 hydrogen over here. So this carbon, look at on this way. This carbon, looking at this way, we'll see the same thing. They have a 3 hydrogen on the back, and they have a 1 inner carbon in between. And this one also same. If you look at the 3 hydrogen on the back, 1 carbon in front of it, and also did the same. It shows a really good symmetrical, like a position they can see. Then they're going to have some environment over here, and also here is as well too. There's a 1 terminal carbon on the back, and inner, and terminal on the back. So in this case, they have only 2 signal will be catched, because only difference with these 2 and these 2. But if there is a carbonyl group over there, okay, then that makes change everything, because this carbon is not the same anymore. They are experiencing different environments there. Okay, so there are 2 are different, and each terminal carbon not looking at the same internal carbon, but this carbon looking at the carbon with the oxygen. This carbon now looking at the carbon with the 2 hydrogens. So those 2 are different. The 2 are also having different environment as well too. So that makes 4 different peaks on NMR. Because each carbons in this compound will have different environments there. Okay? So if that is the case, what you can do, so once again, you don't have to worry about the where you can find the what group on the NMR, because that I'll give you the table on the exam. So all you have to do is just look at the table and find the number and see if there's a peak on that number. If there's one, that's that group there. Okay? So just telling you, you don't have to memorize it, okay? 20. Okay, here. So this is where you can find carbonyl groups, okay? Obviously, this is somewhere you can find some carbonyl group related groups, which will be like some carboxyl group here. You can also find some ester group somewhere here, okay? And you can have some amide groups here too, okay? And then here's where you can find some carbon double bond here. And this is where you can find some aromatic ring carbons, okay? And this is where you can find some carbon nitrogen triple bond over there, okay? Once again, this all will be on the table. You don't have to memorize it. I just want to tell you where is it, because if you look at the one with the oxygen and carbonyl group, they're more on the left side because the oxygen will take the electron away from the carbon. That's why they're in the downfield, meaning they are more de-shielded by oxygen from electron density. Okay, this is why this is the group you're gonna find if there's a peak around this region over here. And this is where you can find some carbon-carbon triple bond over here. Okay, I'm sorry, not here. More onto this side. Okay. So this might be a bit of a long range, like I said on Wednesday. Maybe a little bit slightly different from what table you're looking at the other reference articles. So you don't have to be like perfect on the number. But somewhere in the 1 to the 80. Okay. And then you have some kind of long range too, again, to the carbon, just the oxygen to the single bond over there. Okay. And then you have some groups that also makes the carbon nitrogen bond too. And then also it gives kind of also relatively speaking long range of the carbon halogen group bond too. So relatively speaking, they're kind of less de-shielded. As you can see, they're not so much. And here on the 40, this is where you can see the internal carbons. And this is obviously, terminal carbons will be more shielded by electrons. So this is kind of something you can see on the terminal carbons over here. So if this is the case, so I kind of want you to put this in your mind, that this is more de-shielded by the oxygen or nitrogen. It will be on the left side somewhere. If it's like somewhat just single bond, triple bond somehow, but terminal carbon, which is quite happy with the electron because they're kind of beating with the weak component, which is the hydrogen, so on the right. This is the actual realistic knowledge you should know for this chapter. The other thing I just been telling you today, it's just kind of, just the basic principle knowledge you just have to know for the better understanding. But this is the practical knowledge you should know, okay? So just keep this somehow in your mind, okay? Okay, if that is the case, so now we're using carbon 13, okay? So there I'll show you this one again. Okay, so if that is the case, once again, they're all going to be 4 different peaks because of the environment is different. So now you have 2 terminal carbons here and here, but it should be around 20. Like I said, they're all on the right side. But if you look at the 1 and 4, they're not in the same environment, right? So we can say this will be more on the downfield because of they're close to oxygen. This is a 1 carbon away from this one, right, to the oxygen here. So whenever I put the 2 peaks on around the 20, doesn't matter, you don't have to be very accurate, it's okay. But we know it has to be on the very far right side of the NMR. But this one is more close to the oxygen than this one, so it'll be more de-shielded, relatively speaking, than 4 carbon. So this will be 1 and 4. But it should be in the range of what? Terminal carbon location on your NMR. So it's just a little bit slight change, but because of the relative distance to the oxygen from 1 and M4, 1 would be more on the downfield, which is the left side, than this one, right? Makes sense, right? Good. So this is kind of easy one. You have a carbon that's close to the oxygen and carbonyl groups. that is where we find over here, right? So this is right here. Somewhere, doesn't matter. You can find, actually it's about 208, but who cares, right? Really. I mean, if you find the peaks over here, you just know, oh, they gotta be either carbon with the carbonic groups, and potentially somewhere here, maybe, you know, carboxylic group, amide groups, or, you know, ester group, and so forth. But somewhere here means it's oxygen somewhere, okay, which is very easy. And this one is carbon, so it'll be internal carbon, right? So this is where we find somewhere in 40. So this is carbon here. So now you do really indeed have 4 peaks because those carbon are experiencing the different environments around their neighboring atoms in the molecule. Okay. Somehow getting there, right? Okay. So let's do one more, okay? Let's do one more. So let's do a bit more complicated. Okay. So how about we do 1, 2, 3, 4, and 5. Okay. So this is the this one. So this you have 1 and 2 somewhere in the double bond here. So like I told you before, it should be somewhere between 150 and 110. So I can see they're relatively speaking somewhere close, but you can do. They are in the 2 different. Even though they're in the double bond, this carbon is close to the carbonic group carbon and also oxygen than this one. So there will be not on the same position, but two signal on this 1 and 2. So here and here. And now you can see this 2 is close to the oxygen than this one. So it will be more on downfield, like this. But it has to be in what? Where you can find the carbon-carbon double bond range. But just slightly different because the relative distance to the oxygen from 1 and 2. Okay. So we done with this one here. Okay. So then, oh, this is easy too because this is the carbon right next to the oxygen carbonic groups. So somewhere in oxygen, the 200 position will be just that one, 2, number 3. Okay. So if you look at this one and this one, this carbon is bound to oxygen, but not the double bond like the carbonic groups, but the single bond, where I just told you around here, right? So maybe if you find any peak on here, maybe at 60, that's number 4 then. And this is very easy. Terminal carbon is very happy. It's shared with a lot of electrons. So it has to be around the 20, but somewhat happy. So maybe they're lower than 20. Okay, that's it. So that's it. So if you look at the NMR peaks, and if you just somehow remember where those peaks should be, now it's a very easy game now. Okay, because this is a kind of a, so now you can see those all individual carbons are in different environments. This is kind of one, the internal, but also bound to the single bond to the oxygen. This is terminal. This is terminal, but it's the double bond, and 2 is in the same double bond, but close to the carbonic groups. This is right under the carbon with the carbonic groups. So those all 5 carbons are in different environments slightly. So they will show you 5 different peaks on the NMR. Okay. Makes sense, right? Good. Okay, perfect. All right. So let's try to do the one with the. Like I said, we use the TMS because it has very good equivalent carbon and hydrogen. Let's have a sample that also has the equivalent carbon and carbon too. So if you look at this one over here. So in this case, you have 8 carbons. So be 1, 2, 3, 4, 5, 6, 7, 8. But think about it. I know this one has to be different because this is bound to the bromine, this is bound to the carbonic group, this is right under the oxygen with the double bond, this is the terminal. So I know they are different now, but for this one and this one and this one and this one won't be located in the same position because if you look at this carbon right here, especially this carbon right here, they're bound to the carbon that connected to the carbonic groups, and this carbon is connected to another carbon in the this aromatic ring. And another one, even further from there, is the carbon that bond to the bromine, which is the same thing for this one. This carbon also has neighboring carbon bond to the carbonyl groups. This carbon has also another carbon that is an aromatic ring. If you go further from there, you can also find the carbon and the bond to the bromine as well. So those two carbons will be overlapped in the same position. So this is why these two will have the same environments, same electron density, same location in the NMR. So even though there is 8 carbons in this compound, you're only going to see 6 because 2 will be overlapped. Okay, so let's do this real quick. So once again, this is terminal carbon here, right? So we can just put this somewhere in 20 because even though this is a terminal, it's somewhat close to the carbonyl, right? So if it's in this range, I would say slightly over, down to the 20 or 20, that's okay. And then this is quite easy too, right? Number 2 is right in the carbonyl groups. So somewhere in here, because it has to be very de-shielded by oxygen. Okay, and this one, I don't know if you guys remember this. This is the way you can have what? Aromatic ring carbons here. But those two, okay? So this two be, okay? This is the ones that you're going to have the 4 different peaks on this aromatic ring region, like I said before. As you can see, 4 and 5 are kind of, relatively speaking, larger than 3 and 6 because, as you can see, there are actually 2 signals are overlapped there. But interestingly, those are not in same size though. This is just the nature of the carbon-13. That is also the part that is different from the proton NMR that we're gonna do next week. So just keep that in your mind. You don't have to worry about the peak size, or this is the intensity of your peak, your signal, but you don't have to worry about the actual size, but kind of makes sense somehow. It's still bigger than those 2. So now you only have 1, 2, 3, 4, 5, 6 instead of 8 because of the 2 equivalent carbons you can find in this compound. Makes sense, right? Good? Okay, perfect. Okay, just 1 minute. Okay. So this is why the last example I gave you on Wednesdays was this one. If you guys remember this, this is the Dice rule that shows the more substitute major groups than the minor, that is less substitute. So here's the thing. They all have different carbons, 7, but here, not all different, because the here is the only one that is different. Is this one also what? Overlaps, right? Those equivalent on those 2 carbons. So if whenever you run the NMR for products of this one, this is E2 mechanism, strong base, and organic solvent there, ethanol. And then you're going to have either this one, but you're going to have 7 peaks instead of 5 because this is major, because it's more substitute than this one. This is the tri and di substitute. So that's pretty much it for the carbon. I'm not going to do DPD carbons, which we only use it for how many hydrogen attached to the carbon. That's the additional information we can get. But I think it's good enough for carbon NMR. So we're gonna move on to the hydrogen, which is very similar, but there's a little bit more kind of weird, rule you need to memorize. I'm so sorry, but that's pretty much it. Okay, so I will just stop here.